Hello, everyone. My name is Jordan Miner, and today my literature review presentation will be on EASY, the Ensemble Augmented-Shot Y-shaped learning algorithm. And this is a few-shot learning algorithm as well. So before we begin talking about what EASY is, I really wanted to dive in what few-shot learning is, since it's fundamental for understanding EASY. So right here we have an image of a child looking at a penguin. However, this child does not necessarily know that this is a penguin. So instead of telling him it's a penguin, instead, what if we gave him 3 different note cards? So these note cards contain 3 different animals, and we ask him to identify what the object is in front of him. Hopefully, he will be able to say that it closely resembles this note card, which is the penguin note card. The reason this child will be able to do this is because it has learned how to do object recognition. However, if we were to give the same task to, let's say, a baby, the baby would have really no idea how to do this since it has not been taught or does not quite understand this type of training before. And that's the basis of few-shot learning. So you train with a large data set, and then from there you can give it a support data set from which it can pull from. So let's dive into what those support and training sets are. So how do few-shot networks learn? So the first is the training set. So this is a generic and a large data set. Typical research papers have used Omniglot and Mini ImageNet. So Omniglot uses 50 different alphabets with a total of 1,623 characters or classes. And they asked 20 different people to handwrite each of the characters. So there are therefore 20 samples in each of the classes, which brings our total just above 32,000 images. Mini ImageNet, on the other hand, has 100 classes with 600 samples per class, bringing its total up to 60,000 images total. Then we move on to the support set. So these classes are distinct from the training set, so that means the model has not seen these images. So if you look at the support set on the slide here, we have 4 classes, the elephant, horse, rabbit, and puffin classes. And however, in the training set, we can see that none of these classes show up. So in the training set, we have the dog, seal, and cow classes. And that is a key distinction, that the model in the support set shall not be trained on any of the images it will get in the training set. Next, what we do is we give the model a query image, and this is the image that we ask it to quantify and to identify for us. So hopefully with the proper amount of training, the correct training set, and a good enough support set, it should be able to determine that this is an elephant. And then the most common approach to exploit the knowledge learned by models on the training set is to actually remove the classification layer of your training set. So typically training sets just use a typical convolutional neural network. So you would remove the final classification layer and add your own to the end of it, which is called keeping the backbones. So there are different types of support sets. The typical way you say a support set is K-way N-shot. K-way stands for the number of classes, while N-shot stands for the number of samples. So in this case, we have the elephant, horse, rabbit, and puffin classes. So we have 4 classes, and each only has 1 representative sample or image in each of them. So this would be considered a 4-way one-shot classification set. However, if you were to add a second number of samples, so now each has 2, you still have 4 number of classes, so it's still 4-way, but it would actually be 2-shot for this one, just to give you guys a few examples. So now that we have a really good baseline of what few-shot learning is, let's dive into EASY and what makes it such a state-of-the-art classification system. So this paper came out earlier this year in February, and it boasts a simple 5-step methodology, and it reaches or even beats state-of-the-art performance on multiple standardized benchmarks of the field, as I'll talk about a little later. And one of the key things it brought up is it adds almost no hyperparameters or parameters to those used for training the initial deep learning model on the generic data set. So a lot of the parameters and hyperparameters come from the support set later on. So this is pulled from the paper that shows their 5-step. So we have backbone training, which is the Y in easy, the augmented samples, which is the AS in easy, and then the ensemble of backbones, which is the E in easy. And then finally, you just have some pre-processing, and then we can do 2 different types of classification. So let's get into it. So the first thing they do is a backbone training, which is the Y. And what they did was they used a cosine annealing scheduler, which we can see a representative image here on the right. This is a different paper where I pulled the image off, so the values won't perfectly match, but it gives you more of a proof of concept. So we can see at the beginning of a model, the training loss is high for the cosine annealing scheduler, and you bring it down as the model continues. And then when a new model begins, that kind of shoots back up. I'm following the red line here in the image, and you can see the repetitive up and down motion of the red line, which is the scheduler. And this closely mimics a cosine signal, starting high, going low repeatedly. So that's why it's called a cosine annealing scheduler. So in their paper, they used an n sub 0 of 0.1. So that is the peak amplitude that they started with at epoch 0. And after each cycle, or in this case, the image calls it a model, you reduce by 10% that maximum amplitude. So you get a steady decrease to really hone in on your training loss. And so they use 5 different cycles or models for 100 epochs each. So how that would look is the image uses 6 models for 50 epochs each. So you can see some slight similarities there. So they also boosted a ResNet 12 architecture, which we can see an example of here on the right. And they kept everything the same, except after the fully connected layer at the output layer, they added a logistic regression classifier. So this is why it's considered a Y, is the shape right here. So there's 2 different type of losses that are associated with this model. The first is the classification loss. So this identifies classes of the input samples, similar to what we've been doing all along. So it says if a cat's a cat and a dog's a dog. And then for the other one, the other prong of the Y is the self-supervised loss. So this one retrieves which of the 4 possible rotations has been applied to the input samples. So you might be thinking, where do these rotations come from? And that's kind of what I was thinking when I first read this. And really, when I kind of looked it up in more detail, the self-supervised learning just enables robust feature learning for improvement of the model. So instead of just having one type of loss, the classification loss, if they add this self-supervised loss, the model will be more robust and just be an overall better model. So they accomplished this by doing a 2-step forward-backward pass at each step. And so the first batch goes through the first classifier, so that classification loss classifier, with manifold mix-up, which I'll get to what that means in a minute. And then the second batch goes through both classifiers, so the classification loss and the self-supervised loss. And that has those 4 arbitrary rotations to allow the self-supervised loss to really be able to learn. So going back to what manifold mix-up, this is a regularizer. So manifold mix-up does 3 things for your model. The first we can see from A being the original to B after manifold mix-up, it smoothens the decision boundaries. So we have 2 populations. You have the blue and the red population, and you can see in A how it's a little bit jaggedy. It's kind of more overfit for that model. However, in B, we see that all the boundaries are more smooth, and you can really see those distinctions between the 2 different populations. From D to E, it shows the improvement arrangement of hidden representations and encourages broader regions of low confidence. So we can see those same 2 populations, the blue and the red again. And the black dots in E represent those hidden representations I was talking about before. And you can really just see the difference between the subpopulations from the original in D to E. It just kind of broadens the ranges for it to allow for better representations. And lastly, it flattens the representations. So that's shown in both C for layer 1 and in F for a layer 3. So In the blue is the baseline with no mixing, the orange is the input mix-up, and then finally the green is the manifold mix-up for both these graphs. So you can see that the green goes down at a lot steeper slope and levels off a little bit more before the blue and the orange line. So that really just flattens these representations. And one key thing is these effects are really not well accomplished by any other well-studied regularizer. So that's why they decided to go with a manifold mix-up here. And we'll get into this in more detail a little bit later, but there are optional steps of easy, and this is the only non-optional steps. This is really the foundations of easy. The next is the augmented samples, so the AS. So here we have an image of a dog, and what happens is crops are generated, and then they go through multiple versions of each feature vector, and they end up averaging after they go through that function. So Z is representative of a feature vector, and you can see there we take the average at the end. And during this time, they do 3 different things to the images. The first is they use random size crops. So in this sample, I'm short of space, they only show 4, but they actually do 30 per image. And then they do random color jitters. So you can see that the dog looks a little bit more green than you would kind of expect an image of this type of dog to look like. So what that does is it makes the model not really learn the colors behind it, but more of what those colors represent. So that's the reason behind the color jitters. And then we have the random horizontal flip, where pretty simple, just flips along the horizontal axis. And this is an optional step. Next, we come to the Ensemble of Backbones. So after all the feature vectors have been averaged from the previous step, you concatenate them from multiple different backbones. So we can see that there's different functions that each image will go into, which gives us different feature maps. And the main thing about these feature maps that's different is each of the backbones starts with a different random seed. Just some random seeds, they don't get as great of a start as other ones. So it just kind of really allows the model to optimize the training. And one thing that they wanted to point out is towards the end in the results, they compare using this optional step versus not comparing it. And they really wanted to point out the number of parameters always remains the same. So if they're using the Ensemble of Backbones, each individual backbone that's concatenated will have less parameters. So then, therefore, the concatenation of the feature vectors, the number of parameters in that will match the just one backbone if it wasn't ensembled from a different one. And lastly, we come to the feature vectors pre-processing and classifications. So here we have Z, which represents our feature vector, and it undergoes 2 different transformations. The first is centering, and the second is projection onto the hypersphere. During centering, you just take the feature vectors and you subtract the average feature vector, and you can see that the green, blue, and salmon colors, they get more separation, and overall just are able to distinguish them better from each other. And then for the projection on the hypersphere, you can see how they were originally in the center, and now they follow that nice dotted outline of the sphere. And next, they do 2 different types of classifications that the user can dictate. The first is inductive, which uses the nearest class mean classifier. And the second is transductive, which uses the soft k-means classifier. So there are differences between the 2. The main difference is that transductive classifies all the unlabeled query samples jointly. However, inductive classifies one sample at a time. So there are different reasons why you'd use one over the other. Typically, transductive is when data labeling is expensive, and inductive is when data acquisition is more expensive. So now let's get into the results. So they did a 1-shot versus 5-shot accuracy. So if you remember correctly from the beginning, 1-shot just means 1 sample per class, and 5-shot means 5 samples per class. They ran 15 query samples, and they averaged their results over 10,000 runs. in both inductive and transductive settings. So they had 4 different new state-of-the-art performances. The first was in Mini ImageNet for the inductive setting. So we can see here with the methods on the left, we have our 1-shot and our 5-shot, and then they're also broken up to a number of parameters. So you see the less than or equal to 12 million and about 36 million as well. So you can see for both 1-shot and for 5-shot that the easy outperforms the competition. The next is on the tiered ImageNet, also in an inductive setting. Same situation here. They did get slightly beat out on the 36 million for the 5-shot. However, if you look closely compared to the S2 M2R and the EC, they're very much comparable. And then another thing to note out is S2 M2R is where Easy got a lot of their Y-shaped backbone, which is the one required step of Easy from. So it would make sense why they'd be fairly similar in terms of their results. We also had the FC100 data set in an inductive setting. So we can see, again, the 1-shot and then a slight decrease on the 5-shot, however, still very comparable. And then we have the transductive setting. So the 1-shot and the 5-shot for both types of parameters. And then they also, due to the sake of time, I didn't share all of the tables, but they showcased competitive results on a lot of other benchmarks using different data sets. They were usually pretty close up there to the top data set each time. And next, I want to talk about the optional steps. So this is an inductive setting here. So we can see the 5 different data sets they tried. The E stands for the Ensemble of Backbones and the AS for the Augmented Samples. So they ran one without either of the optional steps on, just with one or the other, and then with both of them, and looked at 1-shot and 5-shot for each of the data sets in the inductive and transductive setting. So we can see here that it does actually make a difference, although maybe not like a huge amount. Like it's for the Mini ImageNet, you have about 0.2. For the 1-shot, that makes a difference. However, it does really show why they made some steps optional. Is sometimes it just doesn't work with the data set or with whatever your support set is. And then lastly, we have the transductive setting. So here, similar thing, we had either a E or AS on or off in all the different combinations. And why the backbone, of course, is always on. So that's why that's not included in these graphs. And you can see that in inductive versus transductive, there are some differences for 1-shot and 5-shot. If I kind of go back and forth, you can see where the folded samples kind of change. But overall, I'd say really running both of the optional steps is typically, from what I've seen from reading their paper, the most likely the way to go. So with that, I just want to leave you guys with my references. So the paper publication is the top one, and the URL for the papers with code, if you wanted to look at their code, is listed as well. I also did a YouTube tutorial series. I watched one on few-shot learning. They had a 3-part, and that was really great, and I encourage you to look at it if you're interested in more about few-shot learning. And for the papers with code, there's a couple, the manifold mix-up and the cosine annealing. They had great explanation pages as well, so those are linked. And then the 2018 paper is what I grabbed the ResNet 12 architecture off from, so that's there for your viewing pleasure as well. So with that, I would like to thank you guys for paying attention and listening to my presentation, and I would love to take any questions when I see you all in class. Thank you.